Hello, and welcome to Lesson 3 in the series, Variables and Functions. In this video, we're going to be mainly reviewing some of the topics we have already covered, going a little bit more in depth into variable types and also functions. Towards the end of the video, we'll actually print out the various data types, and this will be one of the first projects that we can include in our portfolio. If you wish to follow along with the first half of the video, you can. But note you'd only need to include the IO stream, as these other includes will come for the latter half. Starting out, I just quickly want to cover comments again. As I've shown before, 2 forward slashes, or what's known as a line comment, they'll comment out a single line of code. So if you want to, for example, comment out, say, this line of code, just precede it by 2 forward slashes and the compiler will ignore it. They're also useful if you want to, say, make a quick notation, in some text showing that whatever this chunk of code is going to do. So basically a line comment. I think it's self-explanatory. The next comment is what's known as a block comment. This is you want to span multiple lines. So say you got a more complicated program, you want a little bit more lengthy explanation that may span 5, 6, 7, 8, 9 lines. You can use what's called a block comment. It's pretty much the same format, except in this time we're using a forward slash and an asterisk. Then to close the comment, it's just reverse asterisk and forward slash. This is also useful for code. Say we want to block out a chunk of code for troubleshooting or other purposes. Here, I've blocked out these 4 statements. So if I did run and compile the program right now, the compiler would ignore these simply comments and would run the rest of the program, assuming what we commented out wouldn't break it. Just undo those for now. So that's pretty much comments. There are other couple of type we can use, but for 99%, 99% of the time, this will cover what you need. I'm just going to delete this now, so it's a little bit cleaner. Next, we're going to go over variables again. You probably are already familiar with these in the first videos. I've mainly been using integers for like our loop arrays and other common simple inputs. To quickly just go over them again. So here I'm creating a variable A, assigning it type integer. But I'm assigning no value. Creating a variable B of type integer, but this time I'm assigning it the value of 10 at the same time I'm initializing it. So either way is valid. You should also know you could do several types of variables at the same time. The only limitation is per line, they all have to be the same type. So in this case, if you had 5 or 10 integer types you wanted to declare, you could, but you couldn't declare floats, doubles, or others within the same line. Second type of variable is a float. Floats are useful for when you want to represent decimal numbers. So far, we've been mainly using integers, which represent whole numbers. 1, 2, 3, 0, -5, -9, but no decimals. Floats allow us to use decimal format. So in this case, we're creating a variable named f of type float and assigning it a value of 23.2. Next one's double, very similar to float, except it can hold larger numbers. We'll actually get into what the different sizes can hold at the end of our program, but for now, it's just an example of some of the different types of variables. There's also long. Next, by different data type, is a Boolean. Booleans are unique in that they can hold 2 different values. They can either be true or false. True is represented inside a computer as 1, and false is 0. They're good for logical functions. We've already kind of used it in the if statement. If this condition is true, then run the following line of code. Bools are used very extensively in programming, so you'll become familiar with it very soon. Another type of variable is the type char or character. In this case, we're creating a variable named C and assigning it to char, or also known as character. In this case, we're assigning it the letter W. Character types can usually just hold one byte code that represents a character. We can also create like a character array, which acts somewhat like the string. But most of these examples, if we do use a character type, I'm just going to be using a single character. One interesting thing to note too is that internally, the letter W is represented as an ASCII value and not W. Here I've put up the ASCII chart to show the different characters and their values. As you can see here, the lowercase w is represented by the value 119. We will see this again in a bit when I run the code. And the next time I'm going to go over quick, we're just assigning variable a that we created above, integer type a value of 12. I just included this to show you, again, demonstrate the two different ways you can assign values to the variables, either upon initialization or later on in the program. Let's go ahead and compile and run this program. Okay, much of this is just simple to demonstrate what we covered already. The first line of code here, as you can see, we're going to just print out some text. A equals the value of A, B equals the value of B, which we can see here in the corresponding line. Simple enough. Again, noting we declared B early on, and we set the value of A to 12 later on. Simple enough. The next line we show the same with multiplication. A times B equals 120. Third line we show an example division. A divided by B, 12 divided by 10 is 1. Wait a second. 12 divided by 10 should be 1.2. Well, this is an example of the integer division I've shown before. Since both A and B are integers, they only deal with whole numbers. So when you do a mathematical operation that results in a fraction or decimal left over, it just gets cut off. So in this case, the result is 1. If we want to display the actual remainder, or the decimal result, we'll need to input a float into one of the operands. We can do this either literally using a 10.0 as in this example, or more commonly we'd just assign a float or double type variable so that we would get the proper result. Then here we're displaying the contents of bool, which up here we set to true, so internally that should display as a 1, which we do indeed see here. Bool equals 1. Then we're setting in the code bool equals false. And we can see the result of that when we print it out on the next line. Bool equals 0. Then the next section, we're just doing some more math inside the code. A equals A plus 5. This is similar to what we used in our for loop when we incremented. So we're taking the value A, which was 12 up in the code, and we're adding 5 to it. We can see our result here, A equals 17. A little bit further in code, we're dealing with our W, our variable C type character, which we assign to a W. We can see the output here, just the title of the section, character types, character C equals W. But what's interesting to note, again as before, internally the computer is storing that value as 119. Again, as shown on our ASCII chart, internally the computer stores the value as numbers. As shown in the code. How we can access the number is simply by converting the variable c into an integer type. This displays the number instead of the literal character w. We can also demonstrate this by doing a reverse. In this case, we can cast a number as a character. So we got w is 119, x is next character in the alphabet, should be represented by 120. Let's just compile and run this code again and see what happens. And here we can see the output. Character C equals X. Okay, so that is the basic overview of variables, some basic mathematical operation, Boolean, and character types. We'll be dealing with these more extensively in future videos, but for now I just want to do a basic introduction. So for now I'm just going to delete this code. Next topic I want to cover is pre-increment and post-increment operators. We've already used this before in our for loops. As you recall, this syntax probably looks familiar. But there's two different ways. The videos up to now I've mainly used a post-increment, so like I++. But you could actually use a for loop with what's called the pre-increment, ++i. In loops, they perform identical functions. So no matter which way we run this code, it's going to work as expected. At the end, closing brace, since the operation is performed, it'll increment I in either case. Where they are differently, however, is in actual mathematical operations. It's like if I increment I, it's actually going to return I in a different way. How we're used to now is I'm going to return the value of I and then increment it. So if I equals 10 and I print out I++, it's going to put 10, then after the fact it's going to increment. The difference here with ++i is that if I print this out, it's actually going to display 11 as it's going to increment, then return the value. Here's a couple of examples. So the pre-increment operator increments I first and returns the value after the incrementing has occurred. The post-increment operator returns the current value of I first and then increments the value. One interesting aside is that internally, the only version of this that C++ uses is actually the pre-increment operation. The post-increment is actually an overloaded function. We'll cover overloading in future videos. It basically copies the initial value off somewhere before sending the value into the function. So behind the scenes, this is the actually only valid incrementation for incrementer for C++. But when we use this format, basically it takes our variable I, copies it into a temporary holding spot, sends it into the function which increments it first, as shown here. And when the function is complete, it actually returns us that temporary holding space. It's probably confusing now, so don't much worry about it. The important takeaway is, in loops, either format does not matter. Oftentimes, a lot of people prefer this way. But if you're actually doing some operations in code, some kind of mathematical on its own, the order does matter. Again, in this occurrence, you're going to increment it to return I. So if I was 10 and I run this, I is going to be 11 in the operation. If I run it the old way, post increment, and I is 10, I will be 10 for that function and gets incremented after the fact. Okay, we can clear this out. Here's a couple of examples. Just let me undo the comments so I run these again. Got compiler error because I deleted the code above. We can just quickly fix that. Make A an integer. Compile, build again. Here's an example of what I just explained. In this case, A++ is 10. So A returns its current value, then does the incrementing. Then here I'm just resetting A back to 10 just to demonstrate this point. And in the next line, we can see the result of a pre-incrementer. Here A was 10, we're incrementing it, then returning the result, which is 11. Next two lines of code are showing examples of both using loops. The loops are identical, except for in this case, we're using the post-incrementer. In this case, we're using the pre-incrementer. As you can see in the output, they performed identically. So just keep that distinction in mind. Inside the loop logic, since as I showed before, in larger loops, where we'd actually use braces, but the same concept. The actual incrementing does not happen until it hits this closing brace. That's why any code inside will function identically. Where in mathematical operations on their own, they're performed at runtime, right where they're called. So this point can cause confusion for some new programmers. That's why I'm going over it now. And another thing I'll point out, is I explained this briefly in an earlier video, but whenever you use like loops or if functions and stuff, typically we enclose them in opening and closing bracers. That's because normally we have multiple lines of code. If, however, you just have a single line of code, like in these examples, you can get away without the bracers, as it will execute the immediate next line of code, as is what we're in bracers. This would not work if we wanted to try different lines. I just wanted to point that out, as I often code this way if it's a simple one-line statement after a logical check. But either way is valid. I can close this out. Compile and run again. And notice we get the exact same result. Okay, one other thing I'd like to cover is up till now I've just been using like these standard end lines to add line spacing. That helps format out our program, make it a little bit easier to read, break sections of code up. Here we've got the results of that. That is nice and all, but if we want a significant amount of space, you'd end up doing something like this. Which, as you can see, if we wanted to insert quite a few into our program, that can get lengthy and a lot of typing for nothing. One way we can get around this, and this is probably not the most efficient method either, but it's a quick hack. We can create our own function. In this case, I called it just pad output. And we can see that down here. Basically, it's a function of type void, returns no value. Does, however, take one value, an integer, lines. In this case, the number of lines we'd like to pad. So we can accomplish this by a simple for loop. Start with 0, and while I is less than the number of lines which we input into the function, run this output, and again increment it each time once we hit the closing bracer. In this case, we're just simply outputting an end line. So this is nice because, say if I want to add 10 line pads, I can just simply call this function with a 10. Want to add 5, you can call this function 5, 1, 1, and so on. So we run this now, pad output 8. And there you can see we have 8 lines. We would like to move this towards the bottom. And maybe we need, say, another 10 lines. We can just feed the function 18. Build and compile. And we moved it down. Looks like we could probably use a couple more. And there we go. And while this is somewhat of a hack, it is a quick and easy way for these early programs in order for you to clean up your output a little bit. You can just include this function in all your programs where you need additional line spacing, and you can put it anywhere. So if you just want, say, 1 or 2 lines up here, you could just call this function with an appropriate number of lines. Say we want to just do 2, works equally as well. And for now, I'm just gonna, we went over to increments and post increments and shown some examples. So I'm just gonna delete this code for now as we get to the main functionality of the program. I'm just gonna get rid of the pad output in this case. All right, now we pared our main program down to one function call. Uncommon here. Print data types. And that's kind of getting to the main point of this program or lesson that I wanted to get to. We'll be using this as our first demonstration into the portfolio project, which I'll probably start, and maybe the next lesson we'll work on that. But for now, we're just going to print out some of the various data types and ranges used on this platform. And I use the terminology this platform because some of the different computers will use different sizes for some of these values internally. Let's see. Comment to pad output here. Yeah, I'll just leave it for now and show what's going to happen. So we'll compile and run. Hopefully this works. Yes, it does. And here we go. Here's the output of this program. Again, the size of various data types and ranges on this platform. And here's some of the ones that we got. I've been mentioning void a lot, and normally void's simply just an indicator. It's not going to return any value, but it does indeed take up some data on the computer, a 1 byte. So I just wanted to include it to show that. We have the Boolean type, which again can be 0 or 1, true or false. True being 1, false being 0. That takes up 1 byte of space. 1 byte of space, as you recall or may not know, represents 8 bits of data. So in this day and age, 8 bits isn't too big of a deal, but early on in programming, programmers had to be mindful of how much memory they use, as they had a limited amount to work with. But it's still useful as you're doing advanced functions where you need to allocate memory and maybe work with pointers and next memory addresses. But for now, it's just nice to be able to run this program quickly in reference to different sizes and types. We also see our character type, which again is 1 byte. And since internally it's just representing a series of numbers for the character, 1 byte was deemed plenty. There's a wide character type, which can expand the number of characters represented. So this can use different code sets beside ASCII, but we'll touch on that more in upcoming lessons. There's also a short data type, which is an integer, but instead of using the 4 bytes, it uses 2 bytes. And on these, I've also had the program print the ranges. So short can actually represent decimal numbers from negative 32768 to positive 32767. And unless you specify, the data types will cover the negative range and positive range as shown here. There's also an unsigned version of them, which gives you a little bit higher count at the expense of not using negative numbers. A lot of times this is okay. So much of our daily life we live in the positive number realm. Only in computers and mathematics do we venture into the negatives, which of course is popular in programming So you will use both of these, but sometimes just the unsigned version works out well. And truthfully, short is rarely used. Most of the time we stick with integer because nowadays memory is fairly cheap and not quite as important as it used to be. And here we can see the integer range, quite a large value. What is that? Looks like 2 billion, negative 2 billion to positive. And 2 billion. And again, the unsigned version gives a slightly larger range to work with. And here we have long, which in this day and age, it's identical. Used to be integer, used to be a little bit smaller, but depending on the platform, again, these ranges in bytes will be slightly different. But in this case, they're actually identical, so there's really no big point using it. Integer works well. Unsigned long again, and here we have a larger data type, long, which is using 8 bytes of data. And again, the range is quite a bit larger. We also have the floats that we covered, only 4 bytes. And here we can use the floating point numbers as it shown at the beginning. And doubles, also floating point, but in this case 8 bytes. Was again a much larger range. So I thought this would be just a neat little program to run that we can include in our portfolio. As you go on, maybe you delete it because it's really not a huge thing. But at first it might be just a quick reference that you could easily access and see different data sizes and the range that they use. And again, here we got our standard process return, press any key to continue output. If we wanted to clean that up a little bit, that's why one of the reasons I included the pad output function. So here we can just run it again. And it just puts that towards the bottom. A little bit cleaner. And you can use it if you want. Actually, it looks like I put a couple too many lines in. Let's clean that up a bit. Maybe use 8. Use 7. Okay, that's much better. The reason that was working is actually I forgot I was going to cover this. Here's the standard way I've been doing it. So if I comment this out, this will just put 3 end lines into. As you can see, I think you can figure that out. So instead of that, we'll just use this pad output function. Make up for those 3 lines I took out. I gotta uncomment it. Demonstration of the comment functionality. Comment out does not work. Uncomment it. And there we go. So again, just a way to quickly maybe clean up your output. I don't know. You can use it or not. To me, it just looks a little bit nicer putting that at the bottom. Just system standard code. So I have it interfere with our program up here. Okay. Then the next thing I wanted to point out is we can also, and this will actually get implemented once we include this into our portfolio. Right now it really does not matter since it's just running as a standalone program. But there's a couple ways to do this. And up till now I've been using system calls, which actually work perfectly fine for these type of programs. But once you get more complicated programs or something that's actually going to be used in a production environment, it's actually frowned upon to call on the system because there are some security vulnerabilities and it does impart a performance hit. And there's some debate on it, especially now with, how powerful the computers are. If you're just writing something that's going to be used on a standalone workstation, like you're probably programming on now, it probably does not matter. But if you're writing a program later on in your career, in the financial institution or something that needs a lot of performance, you're going to want to avoid making system calls. So I just want to point that out now before I get a lot of comments on, oh, you should never use the system. And for these just homework type assignments, you know, it's perfectly valid. And I think it cuts the clutter out. I mean, you can learn more about the better ways to do it later on. But for now, I'll probably use it, at least in these initial programs, because I think it's just a nice way to get a little extra functionality with, you know, just a couple of one short line here. Like up here at the top, I'm using a system called to clear the screen. So when we had other input above, it wiped that out and would just right away display our thing. So later on in our portfolio, I'm going to use this at the beginning just to wipe out the menu that appears. And when it launches the next section of the program, it'll display a nice clean output like that. So clear screen is pretty much like you think. It just clears the screen, then starts with line 1 right after it. There's another output here. Right now, it's going to seem kind of duplicating because there's already a pause statement when you run these. And that's simply because this console is actually launched by the IDE here. So the IDE is causing this to pause. But if this was ran standalone, it would just open and close right away. So this here, press any key to continue, is generated by the pause statement. Again, we're using the system call, pause. So basically just holds it open until you hit a key. Again, if we tried to run this program outside of the IDE, like if you look this up and double clicked on it, it would open and close instantly before you had a chance to read it. So this is just a way to keep the window open. And in this case, we're just returning any key, and since the IDE holds it up anyway, we get press any key to continue. I just want to point out, well, it's the same syntax. This is indeed different, 2 different functions. And you're probably confused as heck right now, but this will become more apparent as we go on. And just expand upon that topic just a little bit. Since, again, you'll probably hear some people frown on using the system. Another way we can do a pause is kind of build our own. Actually, just let me show you this here. We can just use a standard cin, and there's a get function, which just waits for a key press. So it will pause until it gets some type of key press. So if you run it like this, you can see it's just pause. We're waiting for a get down here. And you can hit anything. As long as an enter, just enter by itself. Then we close out the program. And this line of code, since we don't get the nice built-in windows, please press any key to continue. I just included a prompt. It's a little bit cleaner what's going on. Oh, there you go. And again, in this case, since the IDE is holding it open, it seems a bit redundant. But the need for this will become apparent as we build out our portfolio. So either way, it works fine. I mean, I think for most purposes, just the built-in system pause would work great. But I just wanted to let you realize there are different ways to do this. And even with the clear screen, for now I'm just going to keep the system clear screen because I think it's quick and efficient. But there is a way we can do it totally within C++, where it involves basically writing a bunch of blank spaces to the buffer, you know, how big the console window is. It counts out the number of columns, number of rows, and writes that many spaces to kind of do a behind the scenes hack. But the benefit is we don't have to make the system call. And again, the system call is dangerous too, because on different platforms, like I'm mainly aiming for Windows users here, but in some Linux systems or other systems, the syntax will be different. The system and some of the functionality will not be the same. So again, if you're writing a more portable program, as it calls, something that will run on Linux, Windows equally well, you're going to have to avoid such things. But since I'm assuming most of my viewers are using Windows, for now we're going to be using system. I'm just covering this so you do actually keep that in the back of your mind and realize that at some point, especially if you're going to be doing production code or code that's going to run on different platforms, you may want to avoid this type of programming. All right, with that out of the way, I think we hit that overhead enough. We'll finish up here. The return value 1. Up till now, we've just been returning 0 because, you know, our programs are fairly simple. We're not doing anything. And in main, we're still returning 0. But in this case, I'm actually going to return a 1. And that's going to be used later on. Like right now, it really makes no difference. This could be return 0. And it's going to run identically, because main is not expecting any return. But later on in our portfolio, we'll be using this to indicate whether we want to keep the menu open or just close out of the program totally. So I'm just adding this return 1 statement now. And also, as you notice, since our main here, we're actually calling this, I put all this in its own function. That is because, probably starting as early as the next video, I'm just going to bust this out into its own file, and we're going to incorporate this into our portfolio project. So by having it its function, it's just ready-made to be imported into its own file where we can call this from anywhere. Just like we are here from main print data types. All right, so I think that's probably enough for this video. I do want to try to trim these down in time. But hopefully you got a little use out of it. And I think as we go on, it'll become a little bit more apparent what we're doing here. And I may have covered it, but if you're going to run this, just be sure that you do include these additional include statements up here. Normally include IOStream and everything. Standard libraries for the Windows calls, the systems here, as we showed. And the C limits and C float, that's for the various, to get the size of the work and to get these shorts, you know, the range. And feel free to play around. Maybe just for fun, either omit these or comment them out and see how your program breaks, put them back in. That's a good way to learn, is just experimenting and just seeing what stuff does. You know, comment stuff out, see what breaks, put it back in. Helps get your mind connection to what's doing what. All right, and I think that's it for now, and I'll see you in the next video.